the test. We are here in our notes. We're almost done.
I didn't do the last one. Oh, and I didn't do 9. I need to do the whole number.
It's extra work on top of already having extra work. Time usually like 15 minutes. Oh.
So I only have to do like 4 problems.
Sometimes, like if they're like a really hard unit and it's not a long time to use, then you have to. Yeah. But for like this, I'm like a week later. Yeah. Like you should be able to do 6 again. Okay. I'm gonna turn the light on. This is silver nitrate. Silver nitrate turns your skin black, so that's why I'm wearing gloves, and I'm really trying to preserve it all over the place. It's also really expensive. So
I did that.
Yeah, you did something like this.
I got it on me last year.
I always end up with it.
Did you really?
Like I scratched my eye and broke my eye like a witch meter. Okay.
Subconscious or high?
Cool. Those are moments in my life when my husband looks at me this episode. For how smart you are. It's like not do actual, yeah, real life things. Okay, so we don't even have to use our brain eyeballs. We're going to use our regular eyeballs. Okay, so what I got for you is not this baby come worksheet on isotopes. Although you I have copper solid plus silver nitrate. I don't know why I put that in parentheses. Yeah, I am. Thank you. Aqueous. Okay. So, copper wire looks copper in color. Silver nitrate. Silver nitrate is a colorless liquid. Silver is going to be colorless. We know that there's not actually silver nitrate in here. There's silver ions and nitrate ions. There is no silver nitrate, it's soluble. So I'm going to drop my copper wire in there and let it sit. What I want you to do is with your battle buddy, 2 things. Finish this up, what are the parts going to be, and then do your oxidation numbers. Practice your oxidation numbers because you guys left at 1 today. I'm going to like 3 we did it. Ready, go. I think you're going to ask. How do you know it's copper 2+? Because it's just always going to be copper 2+ for any chemistry, okay? It's like the most common copper, unless they tell you it's like a 1+, assume it's a 2+. How I did this polyatomic inside here is I know the whole charge of nitrate is -1. And so I went from just that, knowing oxygen is -2. I don't know why I said that as +4, that would have to be +5. To make this inside add up to -1, okay? So -6 and then +5 is still -1. That's how I do polyatomics in parentheses, okay?
You just need to remember, like, copper's 2+.
Yeah, and like iron is going to be 2+ too. Pretty much when in doubt, like if it has, it's could be either or, it's going to be the 2+. Okay. Okay, so let's talk about this. Copper started with an oxidation state of 0. It was the solid, it was a metal. It, as a product, then, should go to +2. We call that oxidized. Oxidized means it lost 2 electrons. But it's not magic. Those electrons don't just disappear out of this test tube. Those electrons are then being gained by the silver. So the silver was an ion. It was +1. We could not see it with our eyeballs. We cannot see ions. But then it gained the electrons that the copper lost and went to 0. Oxidation state of 0 is a solid. We call that being reduced. So to our eyeballs, we should be seeing silver metal coming out of the solution. It used to be dissolved, and now it's not. And that exchange of electrons just happens right on top of that copper wire. So that's why it's sort of growing right on the copper wire, because that's where the flip-flop is happening. Yeah, so I went from something that looked like water to silver crystals.
We did it in
Yeah, you did. Okay, yeah. Oh, yeah, you weren't there. Okay. So remember, copper solutions are blue. So my copper is turning back into an ion and turning the water blue. Okay? So I was trying to get the silver crystals off of the wire to see if the wire is there. Yeah, probably. It's pretty, the limiting reactant is not the copper. It's the silver. It's a pretty weak solution. Okay. So, but here's the thing about it. The reverse would not happen. I could not put silver in a blue copper solution and it would react. It would not react. Okay? And that comes from what's called the activity series. So you need to open your book packet for this chart because it's too little in the notes. The activity series is the likelihood that it's going to react. There is quantitative data that goes with it. This just like lists them in order. Okay? So the reverse does not work.
We have to memorize it.
Along the periodic table. The higher up on the activity series, the more reactive it is. Meaning it's more likely to be an ion. Copper and silver are both towards the bottom. They're both actually pretty non-reactive metals. But you see that copper is just right above silver. That means copper solid is more likely to dissolve than silver is. So if copper is more likely to dissolve than it would in a silver ion solution. The one that's higher up is going to react, okay? But silver is below it, so I could not put silver metal in copper solution. Okay? All right, when the music starts, just talk really quick about how this chart works, and then we are going to learn a little bit of math. Ready, steady, go. Thank you. Concentration means solve for molarity. Okay. Molarity is going to be capital M. It's the moles of the solute per total liters of solution. The higher the concentration, the higher the molarity. Okay? We do not have scales that measure in moles. We have scales that measure in grams. So there's going to be some converting, which is why like summer homework is like, can you convert grams to moles? Because in lab, in actual real life scenarios, we do not know moles, we know grams. And then we can convert to moles, get to the concentration. Okay? You will on your first or your second lab on Thursday, so lab on Thursday, you will be asked to make your very first solution. And so I'm going to just give you a concentration. I'm going to say make 250 milliliters of a 0.5 molar solution. And you will have to do it. I will be able to tell if you do a correct job and get correct results. So let me show you how to make a proper solution. This this is a volumetric flask. This is a new piece of equipment. I don't think, nobody has done that all day. I'm surprised. Yeah.
Is that like close up?
Okay, so it's open on top, but it has, like, you can put a stopper in there. It only has one line on it because it only measures one volume. This is a 500 milliliter volumetric. That's all it measures. They come in different sizes. Like teensy cute ones that are like 50 milliliters. You guys are going to use 250. All the way, I have a big 2-liter one when I need to make like classroom sets and stuff. Okay? The line is perfect 500 milliliters. So our scales do not measure in moles, so we need to do some math. So step 1 is always to do the math to figure out how many grams. Grams of solute. All of that looks like soluto, but that's so solute. So you're going to do some math. Probably you want to check with me or people around you to make sure your math's right before you go ahead and make your stuff. But maybe you don't. Maybe one person. So this is me measuring out perfect amounts because this is like the one time that if your math says you need 1.2 grams, like take the time to get 1.2 grams. Because if I want my concentration to be perfect, this has to be perfect, okay? Whenever we make a solution, we always start with water on the bottom, no matter what we're doing. Water always goes on the bottom of the flask. So there'll be gallons out for you, so you don't have to like squirt bottle your way through this. How much water? I don't know, like a smidge. It really doesn't matter. You're going to be filling it to the line anyways. It's exactly a smidge. Start with distilled water on bottom of, we're going to write out volumetric flask because it is a word you need to know. Sometimes on the first response part of the AP exam, you explain how to make a solution. Those are like nice 4 points. And you only need like 50 of them to pass.
That'd be cool if you did a lab, like for the AP exam.
One of the labs will be tested. And it hasn't been this one in a while, so this is a good one to be tested. We practice it. Okay. Water on bottom. How much doesn't really matter. Just put a smidge in. Then what I'm going to do is I'm going to pour my powder in, but do you see? Like it's sort of everywhere. My math says that all of this needs to be in here. So I need to, these are bendy, I need to take the time to rinse this all out. Like get every little crystal out. I get it all out of my funnel. Take my funnel out. I can get all in here because this all has to be in my solution. Okay? Once, let's rinse to get all in.
What's that blue powder?
That's copper sulfate. I picked blue so you could see it.
Did you use that, you think?
Yeah, you're going to make a calcium chloride one. No, you're making an unknown sulfate one. Drew made your calcium chloride. Okay. I need to get this to the line. This is where I guarantee half of you are going to screw up and have to pour it down the drain. It's better just to accept defeat fast and start over rather than like whine about it and be sad about it. I will tell you why. Because as you pour, you're going to be like so concentrated on stopping before the line, sometimes you don't notice that the funnel is filling. So you're like, oh, I'm getting close to the line, I'm getting close to the line, and you stop, and then the rest drains out of the funnel and you go over the line. If you go over the line, there's like nothing you can do about it. You cannot suck the water back out. This water maintenance has already done their things. Just accept defeat, dump it out, and try again. Like, don't waste time being sad about it. This first solution you make is super cheap, and it can go down the drain no problem. I will tell you, your best bet is to stop before the line. Sometimes I even stop before this because I screw up solutions too. And then I take my squirt bottle where I can control it a little bit better, and I fill to the line. Don't forget meniscus. Okay?
Pretty good.
Thanks. Fill to line, do not over pour. If you do, be mad at yourself for like 1 second and move on because you have to start over because you still need to get it done. Okay, so quick somebody remax. These are spinners. These are magnets. These magnets are the perfect size to go down the drain. So please do not drop them down the drain. We're not using them. Stick them to the magnet just so they don't get lost. You'll see me like be your waitress and stuff, and I'll come around, and if I see it sit down, I'll put this sticker right here. This, good, yeah, it does. But they're little magnets. This goes in there, and then you can just turn it on, and it spins the magnet, and it stirs it for you. And there's light feature if you want. If you turn it up all the way, sometimes it just gets a little wild, but if you're a little wild and you want to do that, you can do that.
It looks like Gatorade.
It does. Sometimes it doesn't dissolve very easy. You have to spin it for a while. Some things dissolve super fast. You just have to spin it for a second or two. I'm going to check to see if there's any powder on the bottom. There is not. So I'm going to say that this one is done. But now we have a magnet in the bottom. Don't worry, we have a magnet getter outer. That is not what it's called, but I googled magnet getter outer to figure out what it's actually called. Magnetic bar retriever. That's what this is. This just has magnet on the bottom, so you just stick it in and you can pull it out. Please.
I need one of those in my car.
I know, for like drop cell phone stuff. Please rinse it before you put it back on. Okay, but now look, this drop below the line. When aqueous solutions are made, everybody gets so tucked in from being a strong magnet that this will drop below the line. You need to refill back to the line for your perfect solution. Nope, you don't have to. Okay, spin to dissolve. Remove magnet and fill to line. For a perfect solution. I hope you get it on the first one. It saves time to do it right the first time. When the music starts, please tell somebody how to make a perfect solution. Ready, go. The dilution equation, you've seen this one before, M1V1 equals M2V2. That's if it's already in a solution and we're just trying to lower the concentration of it. The ones are like the original solution. The twos are what we're trying to dilute it to. M is molarity, V is volume. Whatever units you use for volume, just as long as they're the same. It's a proportion. Okay? Let's do some sample problems. So we are going to start on number 14. So page number 14. Number 14 is about your activity series. Okay, so it says, will an aqueous solution of iron 2 chloride, which means I don't actually have iron chloride, I have iron ions and chloride ions, oxidize magnesium metal.
I don't think so.
Don't worry about writing the net ionic equations, but practice your oxidation numbers. Finish it off and then practice oxidation numbers. Let's talk about it. Ready, go. Iron is above magnesium on the activity series. I'm sorry, magnesium is above iron on the activity series, so it's more likely to be an ion. So yes, this would happen because the magnesium is going from 0 by itself to +2. Iron went from +2 to 0. So magnesium went from 0 up to +2. We call that oxidized. It lost electrons, but it gave it to the iron. It's not magic. The iron went from a +2 back down to a 0, grabbed those 2 electrons, and turned it into a solid. We call that being reduced. So if we did this, we would have an orange liquid. Iron liquids are orange, and it would turn colorless with like a rust. It would look like a chunk of rust. Yeah.
This might be dumb, but why is fluorine negative?
It's -1.
Oh yeah, -1.
And there's 2 of them.
Okay, why is it -1?
That's the charge of halogens. -1. Let's take a look at number 15. This one you'll need a calculator for. Get out your calculator. All right. Calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to make 125 milliliters of solution. So molarity equals moles divided by liters. We do not have moles, you'll have to convert. We do not have liters, you'll have to convert. And then divide them out. Ready, go. You never have to show me conversions, milliliters, or liters. There will likely be this follow-up question. And this follow-up question could be a math question, but it's also a thinking question. It's testing to see if you understand the difference between a molecule and an ion. Okay, that's really what it's doing. It's like a vocab question. We know that if we had sodium sulfate AQ, that we don't actually have sodium sulfate. We have sodium ions, valence, so 2 of them, and sulfate ions. Okay, this is testing to see that you know that it's split apart. If my concentration is 1.32 moles per liter of the sodium sulfate, I just did that math, my concentration of the sodium ion is going to be twice as much. It's like taking a cookie and breaking it in half. I end up with twice as many cookies. They're just smaller. Okay? So if I had 12 cookies, then I needed 24 cookies, I would just break them all in half. I'd end up with twice as many. So my concentration of just sodiums, they're littler, but there's more of them. It's going to be 2.64 molar.
So it gets bigger, but you break it.
Bigger chunks, but we're breaking it apart. So this is testing to see if you understand it's breaking apart. Now to math this, you can just mole ratio it. Moles per liter. There are 2 moles of sodiums for every 1 sodium sulfate. If you wanted to math it, you'd end up with moles per liter. So then tell somebody next to you what would be the sulfate ion concentration. Ready, set, go. It'd be the same because it's a 1-to-1 ratio. Okay. Let's take a look at number 17, and we're going to label it lab. This is how you're going to know how to do math for your lab. So our scales do not measure in moles, so we have to do this math. How many grams of sodium sulfate are required to make 0.350 liters of a 0.5 molar solution? This is what I'm going to give you every time when you have to make your solutions. Like, go make it. This is what you have. The trick to these is always start with volume. You're going to be given a molarity. You're going to be tempted to start with molarity, but do not. Always start with volume, and you're just going to convert it through. 0.5 molar means 0.5 moles for every 1 liter. So I'm going to use that as a conversion factor. Liters on top means liters on bottom. And I'm pretty sure you're proficient at turning that back into grams. We just did it. It's like 142.05, right? If you add it up here, 142. The trick is start with volume, start with volume, start with volume. Okay, so go ahead and put that in your calculator. Push your buttons. It's not about push your buttons, it's about being engaged in your learning. Your homework tonight is reactions and aqueous solutions 1, which you've done the front side of it. This is the back side of it. 13, 15, it's on Schoology, 18, and 20. We have a quiz on Wednesday on net ionic equations. So I said try to do them in 30 seconds or less. I'm not going to hold you to 30 seconds, but I'm going to hold you to not that much time, maybe a minute. Okay, so make sure if you haven't done that ionic equations homework yet, you go back and do that and be ready for that quiz on Wednesday. Thursday, labbing, Friday, Form B.